Yeah, I should be making a video, a little extra draft physics video presentation on the subject of light scatter, which is an important another element of this whole understanding of photon thing that I've been doing lately, and arguing for a more reasonable explanation, or at least some conversation with someone or anyone about the possible answers that fits all of the evidence of the different ways photons behave, being transmitted, being reflected, being diffracted, being creating patterns, not being reconstructed. And scatter is one of those subjects, the phenomenon of, and how scatter appears to be somewhat selective. So I thought I would discuss that a little bit, the Rayleigh scattering versus Compton, let's say, which is sort of irrelevant in most cases, a tiny bit of relevance. So I'm going to play some of the Science Asylum. His name is something ludicrous. No. Bill Imbecile? No, that's not it. Well, anyway, yeah, he's got some sort of name. Whatever. That guy. Well, he's not in the picture. So anyway, this is the conversation. Why is the sky blue? They do the generic thing, the science thing, where they just present a bunch of junk and say, there's your answer. And it's junk they were taught, and it's junk they all say because they were all taught it, and they don't bother thinking about it and saying, does that make any sense? So the idea is there's light, and light's a whole bunch of stuff. So whether you think it's these dopey waves or whatever you think it is, it's supposed to be some sort of field vibration, and you got to understand that there's a ton of it. Whatever it is, it's doing it a lot. There's a whole lot of field stretching. Remember, stretching is big. 2,000 atoms worth of stretching distance. Okay, where this field is being vibrated by the photon coming through. And the idea would be is all of these are overlapped, you know what I mean? Photon on top of photon on top of photon. And they could be coming at different phases, that is, at different starting points. So you have a tremendous amount of noise here. I mean, but lots of different photons of different wavelengths all coming in at the same time. Lots of field being, it's the same electric field, right? It's just one field, and somehow this field's being vibrated by all that stuff, and somehow just one electron has the interaction that creates a new photon. It's just not plausible. It doesn't make any sense, and they just keep asserting it as the truth when they have to know. They have to break this into pieces. They have to understand that only pieces of one photon interact with an individual electron. I mean, it's the only rational way to understand this. So anyway, so there's in the game that they're describing is we have the atmosphere, and what the atmosphere is doing is it's scattering. That is, it's changing the direction of the blue light more, okay, than the red light. So the red light gets scattered a little bit, the blue light gets scattered a lot, and that's why the sky is blue, is because the blue light got scattered by a lot, theoretically, and the other colors don't get deflected as much. Therefore, they make it to us, and then we see a yellow sun and something like that, and a blue sky. All right, so that's the starting point, I believe. I believe that's the starting point. You could see some of that, right? Yeah, you could see some of it. That's all you need is some of it. Anyway, all right, so let's play some of the video and then go back to this, I guess. Yeah, that's what we'll do. So I haven't got it all nailed down, but I can give you the things you're looking for, okay? The points of interest.
Enters the atmosphere, it begins to scatter around. However, this scattering is color dependent. Higher frequency visible light, that means light near the blue end of the visible spectrum, is scattered almost 10 times as much as light near the red end.
Now, the tricky part is it could be the same amount of scatter in the sense that there's just as much getting scattered, but there's less blue light, and so the fact that there's less of it as the mass would explain why it doesn't get through. But the fact that the stuff that the rest of the sky appears blue, that is, the light is getting scattered, that means it's coming down this way, it goes this way, and then we see blue over here because it bounces off something that allows us to see it, to turn it back into a complete photon that gets to us as a blue photon. So clearly the stuff that's going distance and then reflecting back to us is only the blue stuff. The yellow and the red don't appear to be doing it nearly as much.
The spectrum. Which is great and all, but like, why? Why does the color even matter? To answer this, we're going to have to go a little deeper into how scattering actually works.
So again, the state is as this is how it actually works, as if they have completed the dissection, they know exactly what it is. Now I'm arguing, they're doing their dissection and they're basically thinking the heart pumps blood and the liver filters it or something. They, kidneys and livers, they got them reversed or something.
I talked a little bit about scattering in this video, but that was for solid surfaces. The Earth's atmosphere is a gas. Almost entirely nitrogen and oxygen gas, to be specific.
Yeah, those are the relevant molecules they've decided, so I don't think there's anything wrong with that decision because they know that it scatters more in the upper atmosphere and the lower atmosphere, and the upper atmosphere it has a lot less of the other gases in it.
Something about these molecules must be important. As it turns out, both nitrogen and oxygen gas have strong resonances and
so that's what they say. So they're, as it turns out. So again, they're saying it as if they've completed this story and it makes sense.
Ultraviolet. Resonances? Right, I guess I should explain that a little.
No, you should explain it a lot because it really doesn't make any sense at all, really. You just say this is a vibration in a field where there's a zillion different vibrations in one field, and somehow one electron says, oh, I understand exactly what's going on, and I'll just make a new photon for you. How about that?
Light, visible or otherwise, is an electromagnetic wave.
So again, they say it as if they proved it somewhere. It's never been proven to be any such thing. It still has, they still have their duality problem where if I do certain experiments, it'll be clear that it's not wave-liking behavior. But they'll just keep forgetting about that whenever it's convenient. They'll just pretend none of those experiments ever took place. And we'll just say it's a wave in some dopey field, even though that doesn't really work for some experiments.
Disturbance in the electromagnetic field. The energy...
Whatever those are, whatever the electric and the magnetic field are, these magical places that get perturbated by the magical now photon, which can't be a thing, it's just a wave in a thing.
From a wave like that can be absorbed by electric charges.
The magical electric charges, which are also the magnetic monopoles, but they don't want to pay any attention to that. They're quite obviously the magnetic monopoles, and they just keep ignoring that.
Like the ones you'd find inside atoms and molecules.
Yes, in this new mysterious place where they're not even in a location anymore. They're just, amorphous little things hovering around a thing.
When the light wave encounters a molecule...
Alright, so the light wave is gigantic. It doesn't encounter a molecule. So again, we're back to the fundamental argument that they're not showing this to the right proportions. The wave is 2,000 times at least bigger than the molecule. So the change in the field is 2,000 times the size of one of those molecules.
The charges inside it will start wiggling. We say that...
So they wiggle, and therefore, and they wiggle how? How do they know how to wiggle? Are they on a little steel stick that allows them to, where the energy is in the steel? How does this mechanical wiggle process take place? How does it know when it goes this far, it has to go back again, and then when it goes this far? How does it know to do any of that stuff? Oh, that's right, you don't have to explain any of that, right? It's only physics. Physics shouldn't explain why it wiggles, how it wiggles.
The wiggling is being driven by the light. And this is a...
So again, it's convenient, okay? Photon in, photon out, and you just say the wiggler did it, and the wiggler, changed its direction by its wiggle factor. Okay, there, done. We don't need to do any more than that, right? That's a good enough explanation.
Very classical effect. No quantum mechanics necessary.
The whole thing is quantum mechanics. As soon as you turn something into a perturbation in a wave, in a imaginary field, you're doing something other than classical physics. Because frankly, there is no classical physics that ever described what any of these fields are. You can't just say the magic field perturbates. That's like somebody saying it's classical physics to think that space and time are, that time is a dimension. So you don't need Einstein. Well, yeah, you do. And it's a nonsense theory.
Necessary. Newton's second law is enough to describe it. The total force on something determines it.
Yeah, you don't need the total thingy there, right? So it's just F equals ma. And again, it's mass and acceleration. And you don't give photons any mass. So why are you talking about the mass, and the speed of the relevant force that's impacting the electron? So then all you have is the electron and its acceleration. How does it accelerate? How does the field make it accelerate?
It's acceleration. Wiggling is a type of acceleration.
Says you. But fine, yes, it's obviously a type of acceleration that undoes itself all the time, constantly, but okay. And how does it do that? How does it know to go fast and then, oh, slow down, stop. Okay, now go back the other way. Oh, now stop. Now go back the other way. There must be something else affecting it. See, the point is these fields have to be made of something. So each thing is creating a completely unique field, and the field is real as bullets, They're real things, not fake things. And so that's how they can change the same thing in different ways, is because each field is contributing a field. It's not a field that's already there. It's not there until you put the bullets in the field, until you put the soldiers on the ground and have them move in a direction. There's no waves, there's no field, there's no nothing. There's nothing until you have a something to do the work. And the reason why they can't say it that way is because they can't explain attraction through that mechanism, because they don't understand that there's a wave of soldiers on the other side of every object that's pushing in the opposite direction. And all they can do in their field changing is change the dynamic of the field, what's in the field. Soldiers going the right way, soldiers going the wrong way. Soldiers on your side or soldiers on their side.
Since it's the electron cloud doing most of that wiggling,
So again, it's just a non-useful description. So let's, I might as well just break here to point out what I think is a more plausible explanation. So nowhere in this will he mention polarization. And polarization, I think, is the key to it. Because what has to be understood is that the higher frequency light, so just think of these, if you have to believe in waves, all right, just understand that the wave has nodes, and that there's a completeness to a wave. And just think of the complete wave as a node, and just think of it as this little thing I'm drawing as a particle, okay, if you have to believe in waves. And so the point is that the wave size this way and this way is dictated by the fact that there's a thing called polarization. And polarization is these nodes being out of position. So your wave is sort of doing this sort of thing, okay? The wave isn't a beautiful thing to witness. It's really a little bit sloppy. So the things are, so if this was the red light, you can see the things are out of alignment. And they can be out of alignment in both dimensions. But anyway, the point would be is they are out of alignment. But the higher the frequency, the lower the polarization. So the red light is twice, okay, as polarized. Can you see that? I can't see that arrow. Okay, so I'll put the arrow here. Alright, so the red light is got twice the polarization of the blue light. So the blue light is this little thing, and the red light is this thing. So as they're traveling through space, and they're all piled up on top of each other, you could sort of get the idea that the ones that are going to get little bits that are going to hit an electron, so say this one's going to hit the electron. This electron's here. So these two missed, but this one's going to hit an electron, and this one's going to get scattered, deflected. That you could sort of understand that the tighter this, the more likely that a second node is going to hit that electron, right? So when the tighter the polarization, the more likely that more than one bit of your signal is going to get broken. So where the red light would have, well, let's just draw 10 of them or something, some big number. So let's just say you got a certain number of them, and the red light might lose one here, it might lose one there. The fact is, the blue light, because it is more lined up and there's less distance between them, you can sort of get the idea that if one of them hits an electron, the second one's going to hit, maybe the third one's going to hit. More of them will hit an electron and be scattered in the same direction. So they're much more likely to hit electrons, because once they hit one, they hit it more than once, and so they're more likely to be scattered because they're hitting the electron. Now, a way to understand that is he's going to show a little bit more of those atom graphics, I believe, with his wobbling theory, and what you can glean from that, like I said, the terrible proportions he has in those images, is that, again, the polarization, the out of alignment, is 2,000 for a red light. It's like 2,000 atoms, maybe more. And for the blue light, it's a lot less than that. And the truth is the atoms have a distance apart from each other. And so in the upper atmosphere, they're much further apart from each other. So they can be, hundreds of nanometers, 1,000 nanometers apart, or more, maybe more, 4 micrometers maybe. Anyway, and they're much closer together in the regular atmosphere. So you can understand when they're much closer together, then this is going to happen, the scattering thing to all the colors of the light. And much more likely, because they're closer together, they're more dense, so you're traveling through more of them, and so everybody's going to be a little more equal. Where you can see that the blue light would sneak through, or if it hits a lot. And so, so the other point I wanted to make is that's just the distance between the atoms. We know that the actual atom is tiny, and that the electron is just a tiny piece of the little atom. So, the number of electrons in the atmosphere is what you're really talking about, because it's the electrons that are going to scatter the light. So it's the odds of hitting an electron, and what are the odds of hitting two of these? Having one photon of energy hit 2 electrons. Like I said, your odds go up. If the frequency is higher, then you know that the electron hasn't had time to move very far away before you hit it again. So the atom can't move out of the position, where clearly it can move out of position by the time the red light gets here. And so not only is the higher frequency make it more likely the atom's still in the same place and the electron, but again, if you've hit it once in the polarization, they're only a little bit out of alignment, you're more likely to hit that same electron again, or an electron associated with that atom, one of the electrons associated with the atom. So even if you don't hit the same electron, you're hitting a place that has electrons, and now you're more likely to hit another electron with the same photon, and another one. And so that's the difference, is the blue light is more broken, because the blue light comes in packets that are more narrow. They're not going like all this. So if they hit an atom, they're more likely to be scattered. Lots of their nodes are likely to be hit. Where if a red one hits the atom, it'll only lose one of its nodes. So the blue light loses more nodes with each impact it makes with an atom, and it's less. So even though it's less likely to hit an atom, it's more likely to hit one multiple times. That would be the simplest way to understand it, because of its polarization.
Should be the mass of that cloud. As for the forces, that depends on how accurate we want to be. Lucky for us...
Yeah, mass of a cloud. I mean, they just don't care. They don't care that they're making up this story that the electron isn't a real physical thing, that it somehow just poofs into space wherever it has an interaction and you create a new universe. I mean, all of that is what they're basing all that mush on. As if the thing isn't a real thing, that doesn't have real position in space, that doesn't have real momentum in space. It's just terrible that they can do this on the non-existent evidence they have. They just don't have any evidence indicating any of that's necessary.
Even the simplest model will make my point. Two forces is enough. One force is the driving force from the light wave. It's an electric force, because light is an electromagnetic wave.
Yes, says you. Based on what evidence, horse? Oh yes, you don't have one.
The other force is called a restoring force.
Yes, now that's what I've talked about many times, about the fact that when you're hitting the electron, it's in tension in the atom. And what you're just doing is changing its position, the direction it moves. It won't move straight. So when the photon hits it, it can't just move straight because it's in tension. So it moves at some other angle out of the tension. It can't move closer to another electron. So if the two electrons are lined up here and here, and you hit it with a photon here, the electron has to go this way or it has to go that way. But it can't go straight. And that's why it changes its position, and then when it goes back to its original position, that's when it gives back the energy, the photon. And it gives it back as a reflection of the energy the universe is producing, actually.
Comes from the bond that holds the electrons in the molecule. Resonances? Yes, we're getting there. Notice these two frequencies are different.
Yeah, and they don't know these two frequencies. That's why there's a whole bunch of QEs and blah, 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 blah. It's because they don't know any of that.
One in the driving force is the frequency of the light. The one in the restoring force is the resonance of the molecule.
So, right, they're just making this one up and saying it's a more compatible resonance. So they're just kind of making it up. And what's really the factor, again, the thing that's making the frequency relevant is the fact that the frequency means the polarization is narrower. And having the narrower polarization means you're going to hit more nodes of the photon. So any impediment hit is going to affect more elements of the photon, the more refined the photon is. If you could, it's hard to draw an accurate description of what the filter looks like, because the filter is kind of a bizarre filter, right? I mean, little bits very far apart, the atoms, and then the atoms have electrons that have some proximity. And again, like the argument I'm making is that, especially with oxygen, they're positioned nicely around the outside, very geometrically, and sort of in pairs, and well, not pairs. But anyway, pairs, electron pairs. Sorry, brain fart. But the idea is that, yeah, so if you have a narrow polarization and you hit an atom, it's likely that more elements are going to hit other electrons in that atom. Not only the same electron, but others. Because you have more electron density in the places it has impact.
That's the frequency the molecule naturally wants to wiggle at. The closer the frequency of light is to that resonance, the bigger the wiggle. Since color is
the bigger the wiggle. It's obviously a faster wiggle, so it wouldn't be a bigger one. But whatever.
Directly related to frequency, the color matters. So how do we get from absorbing to scattering? That wiggling creates its own light. As we said earlier,
by the magical create your own light mechanism. So again, there's no explanation for why moving an electron, jiggling it, creates a photon. Now I'm obviously arguing that it sort of does, in the sense that when you move the position of the electron, you change its place in space, and now it's reflecting to the rest of the world a different world. So if I did have a mirror and I could move the mirror forward and backward, okay, and we had a substance that we actually did have between us, you would know the difference. If I moved it back and forth, you would get a different impression of the world from the mirror. But I don't need to have an ether, and I don't need to have a field to do that. All I need to do is fling stuff that can bounce off the mirror and tell me how far away the mirror is. I just shoot radar at it, and I can see when the mirror moves, and I can see it on a signal on a piece of paper or on a oscilloscope. I will see the mirror moving by hitting it with energy and seeing it that's in different positions. And the different positions mean that you create, if you keep a constant rate of change in the position, and you put those bits hitting a surface at the same time, they will appear as a photon. Lots of forces hitting us all the time. That's what gravity is. And only part of it is in the form of a constant frequency. And the frequency has to be maintained for at least 6 to 9 nodes. And if one of the nodes is missing, no photon.
A wiggle or vibration is a type of acceleration, but accelerating charge emits light.
So this is the whole other foundational theory of theirs, this idea that all you do is this charge doesn't do anything until I move it. Then all of a sudden it's relevant. And no, it's relevant when you move one. You're changing what the universe sees. You're changing the location of the mirror. Every time you move the charge, you're changing where it's reflecting to the rest of the world, where the light comes from. And every time I move it, I'll change where the light comes from. And if you have the right way of receiving that information, like radar, you can tell that it's moving. Okay? But it's something real that's transmitting the information, and they know that because they know it's moving the speed of light. So it is a photon. They call it a virtual photon, but it's a photon, and there's visible ones and invisible ones.
That's how light is made. Yes, for real. When the incoming light makes the molecule wiggle.
So yes, for real. I mean, they just keep asserting it. Just, minions, stay with me, just be part of our Borg, and this is and they don't need to do anything but this is all they have to do to convince people, they must be right, is to wear a lab coat, have a bizarre sense of humor, and childish even, and do this nonsense. And they just follow right along. Even though it makes no sense. There's no mechanical mechanism anywhere in there. So, look, I put a wave in that's much smaller than the actual wave. The actual wave is 2,000 times bigger than that. Okay, but I'll just pretend that's what the wave looks like. Even though it's 2,000 times that size.
That wiggle creates its own light. Except...
And it creates its own light going the wrong way somehow, which isn't the truth either. The electron changes its position, and if it changes its position straight, then you get nice transmitted light. Okay, but if it goes crooked, then you have deflections, dispersions, scatter.
This one-dimensional picture isn't quite accurate. The truth is, we live in a three-dimensional world, and that new light goes out in almost all directions. It's called dipole radiation.
Which is more nonsense, right? I mean, it's more gibberish talk, because the electron isn't a dipole. And the truth is, the radiation, if the radiation hits something this way, well, you kind of know it's, the idea is it isn't coming straight back. It's likely to be deflected this way or this way. Because when I hit the electron's not going to come straight back at me. It has to move forward. So we know that the scatter is going to generally be forward of the motion of the photon.
And it's very relevant to Rayleigh scattering.
Again, and the point also to recognize that I didn't point out here is when the electron moves, it moves a lot slower than the speed of light. And so that's what messes up the phase of all the little broken bits. And so when you put the broken bits back together and you end up making a photon, you're doing it because they share something in common. They both were slowed down by the same amount of moving an electron a certain amount of distance at a slower speed, and that's why they can be put back into phase.
Let's keep things as simple as possible and imagine sunlight as a bunch of parallel wavefronts. They represent the peaks in the electromagnetic wave. When they encounter an air molecule, that molecule will absorb some of the energy and emit it.
So just no description. So you got these graphics that just don't make any sense at all. We know there's a zillion waves. So when he shows this little wave coming along all by itself, it doesn't reflect the actual change in the field. The actual change in the field is there's a billion of those little things, all waving at different points and different times, all moving, in different little pieces of the space. So the field in all the different pieces of the space is moving in different directions.
Its own light with wave fronts that look like this. It's emitted in every direction except the wiggle axis. But don't forget about the resonance. Because the molecules wiggle more when the frequency of light is near that resonance, more of that light will get scattered.
So it doesn't have anything to do with the polarization argument. This is the rational one. What's the real difference between red light and blue light? And the real difference, the only difference that you can really make this story make any sense, is to understand that the polarization means that there's going to be more when there is an interaction. It's a more complete interaction for the blue light, and it's a lot less complete for red or any other color.
There's a color preference, and as we mentioned earlier,
and it's held true by his original diagram, right? I mean, the purple light even more, the ultraviolet light even more. So if he drew the rest of the spectrum in there, the truth would be that, yes, the tighter the frequency, the smaller the polarization, and the more likely that there will be a complete interaction between an atom and the photon, and that the photon will hit one or more electrons inside the atom, the same atom, and therefore more likely to be catastrophically changed in its direction.
The resonances for nitrogen and oxygen are in the ultraviolet range.
So they just made it up, like, okay, because that works. So this is circular physics, right? Their wrong theory proves their wrong theory, so they're both, the AB is the BA in the other formula. So, it's self-proving, or however you want to describe it. I mean, if you accept that first axiom, that'll create the evidence for the first axiom eventually, because you'll confirm it by saying, well, look, it has the same resonance frequency. Well, yeah, you demonstrated that by this false claim that this is happening, and now you're just going to say that's the reason why it's happening is some external proof, when you don't have any external proof. The only thing you have is you saying A comes first and then B comes second, so you've made a rule, and there's no reason it can't be otherwise.
Blue is closer to ultraviolet than red. Blue light scatters more. Almost 10.
Yeah, we already know that. So they know the outcome. And so they're just engineering mush talk to fit the outcome. Now, that's all we have as a way of deconstructing something. But I'm just saying they're not putting in the obvious. And what's the obvious difference between blue light and red light? Oh, that's right. The blue light is traveling a much straighter line. And huge difference.
Times more. Except that's not the whole story. You gotta talk about wave interference.
So this is supposed to be funny when it's kind of on the edge of a bad joke.
You're right, as usual. The truth is, Rayleigh scattering only happens in the upper atmosphere. It requires the molecules be very far apart and random.
Yeah, the further apart they are, the more it becomes a factor that the thinner your polarization, the more likely the photon is to be completely scattered by a single atom. So if a single atom's going to scatter at least half of it, more than one node will be affected. So it's just about how many nodes in the ray, okay, that are deflected. And so the further apart I put the atoms, the more necessary it is for there to be scattering of a photon that can be recoverable, because you need to scatter a bunch of pieces and shoot them all in similar directions for them ever to be reconstructed. And so the more a single atom's doing that, the more likely you are to reconstruct that atom. I mean, that photon. So it's completely consistent that polarization would say, yes, the further apart I put the atoms, then the less I'm going to damage the red light, because I can only knock a node off here or a node off there, barely even touch it, barely even harm it. Where the blue light, yes, it's going to crash right into an atom, and boom, 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 all the nodes are going to be affected by the atom.
Placed. Down in the lower atmosphere, near the surface of the Earth, the molecules are only 3 nanometers apart. But the wavelengths of visible light are in the hundreds of nanometers. That means we also...
Yeah, 3 nanometers apart, so they're very close. Very, very close. So obviously the light's being transmitted from atom to atom, but it does it very efficiently. So that's part of what has to be understood, that the atoms, as much as they're jiggling, they're not really moving all over the place, because they do transmit the light in a rather straight line of electrons. So as much as the atmosphere is thin, it's pretty thick in the sense that it has to create a pretty straight path, so as little movement of the electrons as possible consumes time, because it's almost, as light travels almost as fast in atmosphere as it does in space. So the atmosphere has got to be doing it really efficiently. That is, it can't be taking any turns. It can't be the electrons being moved, and that's transmitting the photon. They have to move very fast, and they can't move in inefficient directions, or that would really slow it down. Where in glass, for example, it is not being transmitted very straight, even though it's being transmitted coherently from surface to surface. You have to assume either the electrons are moving very slowly from one place to another, or they're not taking a straight path, because they do consume a lot of time for the energy you get from one side of glass to the other, where the atmosphere isn't anything like that. So when they say jiggling and all that stuff, this jiggle is just a tiny little jiggle. It's not much movement at all.
Also need to worry about wave interference. If all these molecules are becoming their own little radiators, and their spacing is only 1/100th of the wavelength...
So let's understand, they're all radiators just by existing, because they have an equilibrium with the universe. So anything that hits them, they give back eventually. And so they're just giving it back based on their motion, and if they change direction, they have to be hit by a force to do that. So they're just being jostled in a field of energy.
Then the chances of one molecule being half a wavelength away from another are extremely high. 2 waves that are half a wavelength out of phase will interfere and cancel each other.
Yes, which doesn't have really anything. There's no cancellation. There's either you break a photon and you put it back together again with other pieces. You make a little Frankenstein photon out of the pieces, or you don't. So the photons of the red light that have little bits broken off, 2 of those can line up and in the right phase, because they both hit electrons in their path, or the same number of electrons, got slowed down the same amount, and ended up reconstructing a photon. So you can remake photons after they're broken by having to go through the process of traveling through a bunch of electrons. And if the electrons are not coherently tied to each other, then the angles of scatter are all over the place. If they're coherently tied to each other, then you have some hope of transmitting the energy in straight lines, and the light survives the process.
It's called destructive interference. This will happen most places throughout the air, leaving only the forward-moving sunlight. Solids and liquids are even denser than that, hundreds or even thousands of times denser.
Right, and density has a lot to do with this ability to transmit, but it also has to do with the function of crystals, and it gets a little more complicated. So that's what decides the reflective index. Isn't just density, but the shape of the atoms.
That's why in most substances, there's only one path for the light, the refracted path. To stop this kind of interference, we need the density of the air to be extremely low. The molecules need to be separated by at least a whole wavelength for Rayleigh scattering to occur and not cancel itself. That only happens in the upper atmosphere. All the blue you see in this image is coming from up near space. The light only scatters around for a bit. As it reaches denser and denser air, its path straightens out.
Well, its path, it still has to hit something to end up getting back to your eye. So, whatever its path, the point is the photon of blue you do see is a photon of blue that's not coming from the sun. Obviously, it's been already scattered in a direction. It has to be rescattered back to you. So it does have to hit a water molecule or some other kind of molecule in the atmosphere to be scattered back to you again. So the sunlight comes in, the blue hits a lot more electrons catastrophically. There's no other way to say it. It hits the same atom more times, more likely hit the same atom more than once, and because it's more likely to, it sends bigger chunks of scattered light, and those bigger chunks of scattered light can recombine, hitting some water molecule someplace else. They'll be coming from different areas. They'll recombine, create a real photon again in the right sequence, the right frequency, and that'll come back to your eye.
By then, though, the blue is coming from all directions. Also, technically, the sky isn't blue, it's bluish-white. While blue is being scattered more, all the colors are being scattered a little bit. All the colors together make white, but white dominated by blue is bluish-white.
Yeah, but the white also has a limit to its scope. That's why it's bluer on the horizon than it is the closer you get to the sun. So, there is a yeah, I don't know, that's probably enough said. There's obviously less of the white light, and it's I don't want to say less durable. Now, that's probably enough said.
This also explains why the sun looks yellowish when it's actually pure white. The direct light from the sun is missing the blue because it got scattered away to the rest of the sky. Also, sunset...
Also, it all got scattered. So all of it's scattered. You're not getting any light that hasn't been scattered, essentially, except maybe some percentage of the sun's actual beam that when you look directly at the sun, you might be getting some light that didn't hit any atoms. But it's all hitting some atoms, and it's all being reconstructed. Photons that were separate have been broken, and the broken photon, your pieces, are what you're going to recombine to create a new photon. So it's always, the same photon. It's just pieces, and the pieces will recombine and make photons, but it can be made out of different photons. I mean, it's hard to say broken because it's all cannonballs. So it doesn't really matter if you make it's just cannonballs hitting at the right rate, and that's it in an amount of space, and that's a photon.
And sunrise look yellow and orange for the same reason. The light travels through the upper atmosphere longer at that angle, which means more Rayleigh scattering. So much, in fact, that the blue is scattered away from your eyes completely. But why is the sky blue and not...
I didn't really explain that part. I have to think. It has to do with the angle it's going through the upper atmosphere, so it doesn't really... Its angle is pitched so much from your eye, the perpendicular to the sun, that you don't see it because it's going really perpendicular, where when the sun's above you, you'll see the blue because it's mostly scattering perpendicular, and so it's got a whole lot of atmosphere it can reflect off to get back to you. But if you turn the perpendicular this way, obviously going that way, you're not going to be able to see it reflect off something because there's less chance of that. It's not going to get back to you.
Purple. Right. I almost forgot. Okay, one last thing before we finish up. You can see from the visible spectrum that there really isn't much purple. Purple or violet is the color on the very, very edge, right around 400 nanometers. It's actually so...
Well, it's actually not. Yeah, that's the trick of it, right? I mean, blue and red isn't actually purple. much as you like to say it is. There's a difference between violet and purple. And I guess they should call the light on the other side of blue something else. But it is curious that it's a derivative, but it's not really made out of red and blue.
Close to the edge of the human visible range that some people can't even see it. The purple colors that most people see are just combinations of red and blue, like this magenta color, rather than actual monochromatic purple. The sky is scattered.
Right, you should have used purple. I mean, you mix red and blue and you do get purple. So, I mean, it's no denying the fact that it's an illusion. It's not real purple. It's fake purple.
Ultraviolet light, too. A lot more than visible light, actually. The only reason the sky isn't purple is because purple isn't very visible. It's there.
No, the reason why is because the purple's getting deflected even more, scattered even more than the blue.
There. We just can't see it. So why is the sky blue? It's blue because of Rayleigh scattering in the upper atmosphere. Sunlight drives the motion of electron clouds inside of air molecules. That wiggling generates its own light that goes out.
So these animations, I mean, you think this is really how it works? That it's something like this, that some plane moves through the surface and it blobs and it does all. Do you think this is really what's happening? Come on, people. I mean, they're so confident, and yet this is what they're showing you as a model. Like, oh, okay, this is our best guess to what it might look like if we could, shrink ourselves down and see it. Do you really think that's what's happening?
In all directions. Since these molecules resonate in ultraviolet, blue scatters far more than red.
So again, just made up. They don't know nothing about its resonate nonsense. And again, it doesn't have anything to do with how it... See, this just has to do with the size of the particle. So as small particles always deflect high frequencies more. All right, that's the rule. So you can do this with regular water drops, big drops versus small drops. The small drops will scatter more of the higher frequency radiation. That's the real catch. It doesn't have anything to do with any resonant frequency of oxygen and nitrogen, or even a particle of dust ability to resonate. It has nothing to do with its resonating ability. It has to do with the fact that the higher the frequency of light, the narrower its polarization, and the more likely it is to hit the same piece of dirt more than once. And that's the reason.
If the molecules are far enough apart, this new light will continue to scatter, and ultimately arrive at your eyes from all directions, which makes the sky appear blue from all directions. And now, you know better.
So says you, I know better, right? So says this is just, I mean, it's a terribly dishonest way to teach a subject. They really don't have enough evidence to be this confident. If people did this in other fields, like, historians take a lot of leaps, right? They find one gold cross somewhere and they say, Rome was here for 70 years. They just, make up a story. So yeah, they're guilty of a lot of shit. But I mean, biologists could never get away with making up these fantastic stories about, the evolution of animals or something. I mean, this is just all made up.
Wait, why did I just say that? Anyway, did I go deep enough for you? Let us know in the comments.
So you show me a superficial, wacky animation that can't possibly be the real thing, right? It's not fooling me. I mean, it looks like a cartoon. I mean, it's no chance the real thing is doing any of that crap. Do you really think that's what it really looks like? Like I said, if I could make a little tiny camera and I could take a picture of it, do you really think that's what it looks like?
Thanks for liking and sharing this video. A special thanks goes out to Fabio Manzini.
Oh, fuck that. Alright. People, they just pile money on top of these Ken Wheelers, all these wacky crap physics. Give me more crap. More woo. Shit, it's so annoying. All right, anyway, that's enough of a critique. Look, everybody's just trying to do their little thing. So he obviously believes this stuff. He fell for it. And so he's just trying to help everybody else fall for it. But I'm just saying you have to see the root of the lack of integrity to all this. Because he's got to know, they have so little evidence to back any of this stuff up. We know the resonant frequency of the oxygen molecule. Blah, 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 blah. Sure you do. You know it because it's the only way your theory can work is if you assign it. Okay? But again, you can, like I say, you can know there's something wrong with what he's saying because you can know that the particle size is what matters. And that vibrating theory doesn't have much to do with the particle size, irregardless of its mass. Well, its mass matters because the more mass it has, the more electrons it has, and it's just about how dense the electrons are. The more dense the area of electrons, then the blue light is going to lose a lot more nodes than the red light. Just a fact. Okay, I've done my job. Please be reasonable. Please. Please.